Hello, and welcome to the Software Engineering Institute's webinar series. Our presentation today is When Measurement Benefits the Measured. Depending on your location, we wish you a good morning, a good afternoon, or good evening. My name is Shane McGraw, your moderator for today's presentation, and I'd like to thank you all for attending. And now I'd like to introduce our two featured speakers for today. First, I'd like to introduce Mark Kasnick, and Mark is a senior member of the technical staff at the SEI within the Team Software Process Initiative, or TSP, and he is in the Software Solutions Division. And since joining the SEI in 1994, his work is focused on transitioning performance improvement technologies into practice through applied research, course development, coaching, and training. Our next speaker will be Bill Nichols, and Bill joined the SEI in 2006 as a senior member of the technical staff. He is currently a personal software process instructor and team software process mentor coach, and he is also in the Software Solutions Division. And prior to joining the SEI, Bill led a software development team at Bettis Laboratory near Pittsburgh. And now I'd like to turn the presentation over to Mark Kasnick. Mark, all yours.
Okay, thank you very much. Hello, I'm Mark Kasnick. Glad you could be with us today. To get started, what I'd like to do is to throw out a question to all those software engineers out there. What I'd like you to consider is, does this cartoon, this situation that you see in the graphic, does this cartoon resonate with any of you out there? That is, can you relate to this type of situation? Maybe just a little bit? Yes? No? Well, let's look at some data. This is from a 2012 KS report on the state of software engineering. I realize this looks kind of bad, but what I can say is there have been improvements. There have been actual improvements in these statistics over the last 10 years. But still, only 39% of projects are completed on time and on budget. 43 of the projects are considered challenged. That is, the projects were completed, but they were over budget or late, and they offered fewer features than they originally specified. 18% of the projects were canceled at some point during the development cycle. Not so good. Okay, this is a different survey, another data point. The first two figures are pretty much similar to the KS report findings that we just looked at. But take a look at the last figure here because it is directly related to quality performance. 33% of IT leaders state that at least 25% of their budget is spent addressing rework. That's at least 25%. Of course, this is a tremendous resource drain of an organization's ability to deliver functionality and business value. So do we have a problem here? Well, when you see numbers like this, it can't help but to make you feel that as a community, we need to do better. This is from a recent InfoQ interview with Capers Jones, who I'm sure many of you have heard of. He's a well-known researcher and author. From on-site interviews with hundreds of software organizations, he draws the conclusions that you see on this slide, namely that when compared to other technical teams within their organization, software teams are not getting much respect from their CEOs. And this is due mainly to a failure associated with the lack of engineering and product development discipline, especially in the area of measurement, which is a topic of our webinar today. When you think about it, can you imagine what the performance results of other technical areas would be if measurement wasn't considered an integral part of their domain? Of course, measurement is considered an integral part of any other technical area. It's just taken for granted. And when you think about it, measurement is actually an integral part of all of our lives. We're measuring all the time, whether we realize it or not. For example, think of yourself driving down the road, looking outside your front windshield. When you see the brake lights go on for the car up ahead of you, when you see that happen, you quickly unconsciously, you measure the distance to that car visually. Why? So that you know whether you need to hit your brakes or not. That type of subjective measurement is what Jerry Weinberg referred to as first-order measurement. It's qualitative and it's fast. It answers the question, what seems to be happening? We use this type of measurement all the time. Now, if you are driving down the road and you notice a car with a red light on the top of it, a police car, you probably would shift to second-order measurement. You would actually look down at your speedometer on your dashboard to see how fast you're really going, and then make whatever adjustments you need to avoid getting a speeding ticket. Now, third-order measurement addresses measurement trends and patterns. Let's say I'm going to buy a new car. I wouldn't really want to rely on first-order measurement, the opinion of my neighbor about his car. I would probably go beyond that. It's a big purchase. I'd go beyond first-order or second-order measurement. Instead, I'd probably use third-order measurement. I'd want to see statistical data on performance of past models of that type of car I'm considering, because it's, like I say, it's an important decision. So the type of measurement that we use should be a function of the type of decision-making that we need to make. And if you're wondering what those guys up in the slide are doing with their first-order measurement, they're just licking their index finger and holding it up to check the direction of the wind. A good example of first-order measurement. Very subjective and qualitative. Now, at issue, with the software development, here's what we're seeing. Decision-making is largely based on first-order measurement, at best. Quite often, claims made about the effectiveness of development approaches are based on perceptions and whatever the new fad happens to be. Now, if we want to mature software engineering into a real engineering discipline, then we need to elevate our game in the measurement arena and become more like other engineering disciplines, other technical areas, where the use of second and third order measurement is taken for granted. So that's what we're going to be addressing in today's webinar, elevating our game with measurement, and we'll do that from several perspectives, including at the individual level, the team level, and then briefly beyond to the organization and community level. So let's talk about you, the software engineer, and how you can use measurement in a way that benefits you personally. Now, I'll bet that some of you out there, you play sports. You play golf, compete in races, go bowling, lift weights. If you do, then you probably keep track of your performance. Perhaps it's as simple as, I knocked off 3 strokes from my golf game today, or I clocked in on my 2-minute mile 16 seconds faster than yesterday. Athletes measure like this because they want to know whether their performance is improving or declining, and how their performance compares with their own personal best or with the performance of others. This is the type of measurement, feedback measurement, that is valued because it drives action. It helps you achieve your goals. If a measurement doesn't drive action, then what value does it have? So the question is, can software engineers use measurement in this way? More specifically, do you use measurement in this way? So let's conduct a little poll. I would like you to answer the following question. The scenario is that you have been asked to estimate how long you believe a new task is going to take at your work. Select the response that you believe is the typical approach that you would use to help you provide the estimate.
Okay, we got 50% as the second order, first order at 36%, third order 14%, and none of the above at 1%.
Okay.
So back to you.
Interesting. I wish you were here with me so that we could have a little discussion about that, but we'll do the best we can. Well, should you be using measurement? I'm glad to hear that a lot of you are, according to your responses. Yes, we should be using measurement, and it should go beyond first order measurement. And why do we need measurement? Well, The reason you need to use measurement is because you need it to make good decisions about how you manage your work. That's basically why you need measurement. Now, I can hear a lot of you out there. I can imagine what you're thinking. Isn't it the manager's job to manage my work? I'm an engineer. I do engineering work. The manager manages the work. Well, not exactly, and I'd like to talk about that a little bit. The approach to management has actually evolved over centuries to this day. As you see on the slide, what has driven this evolution? Management approaches have evolved because there's been an evolution of the worker, way back from the hunter-gatherer to the technology professional of today. That would be you. A major turning point in this evolution was the advent of the Industrial Revolution. You see, prior to the Industrial Revolution, work was performed by craftsmen who had learned their jobs through lengthy apprenticeships. They made their own decisions about how to do their job. They didn't have any bosses. There was no standardization. But now they were in the factories. At the same time, you had many unskilled and uneducated workers flocking from the fields to the factories. As you can imagine, operations were rather inefficient during this transition. It was in this type of environment that inspired Frederick Taylor to write his book titled The Principles of Scientific Management, also called Taylorism now. Taylorism took away the autonomy of the craftsman worker and converted labor into a series of simplified steps, simplified jobs that could be performed by unskilled workers. Taylor's main premise was that the knowledge about how the work should be done existed only among management. That is, managers think, workers do. That was the dichotomy that Taylorism brought to the workplace. Well, that worked okay for a while, but the world was rapidly changing and so was the nature of the worker. After World War II, more than 50% of veterans used the GI Bill to obtain a college degree. By the late 20th century, there were major changes, social, economic, political, and technical. There was a significant shift in how work was being performed due to the technical innovations that were coming about. The advent of this knowledge age really brought a real shift in terms of how work is viewed and managed. With manual work, you can actually observe the product being constructed. However, knowledge work is much different. The work is done in the head, and so you can't really see it being performed. It's intangible. Management can't see the work performed like they could when they were managing manual work. So in a real sense, they lost their ability to manage this type of work, this type of knowledge work. So, the basic tenets of Taylorism, well, they have become untenable in the knowledge age. It's now really up to the knowledge worker to manage the work, because the work is in his or her head. However, with this new reality, there needs to be an attitude shift on the part of the knowledge worker. Knowledge workers, that would be you, the software engineers, must take responsibility for managing your work. So that was kind of a long-winded response to the question posed by the guy in the blue shirt there. But in summary, no, it's not the manager's job to manage how you work. Management provides goals, but managing the work is really your responsibility. You're the one that needs to have control over the way you do your work. And to do that, you need to plan your work. If you want management to trust your plan, you need to make an accurate plan. To make an accurate plan, you need to have data. Otherwise, you're just guessing. To have data, you have to measure your performance. So you see, measurement is a good thing because it can help you to better understand and manage your work. However, this is not true. It's a data collection fallacy. Let's not take this too far. Metrics are good, but the fact is, for a software engineer to be able to manage their work, there are only 4 measures that you need to collect. The size of the product, the actual time you spend on a task in your plan, we call that task time, The defects, you need to track the defects to manage quality. And schedule, that's the date that you complete a task. 4 basic measures, that's it. You first estimate these measures during planning, and then you collect actual measurements as you work. Because you're collecting these measures in real time, they're very accurate. By collecting these measures, you can answer all sorts of important questions about the status of your schedule and the quality of your work. Now, one thing that I want to emphasize here is that we are talking about measurement that is collected by you and for you. They're for your benefit. They're not something that you really need to share with others, unless you want to. Now, data collection like this would be impractical. I think we all agree about that without tool support. And tools have been developed to support this type of data collection, facilitating the entry and analysis of the data. As an example is the Software Process Dashboard. It's a free downloadable tool that is specifically geared for collecting and processing the 4 basic measures. The tool converts the data you collect into a variety of useful derived measures and graphic indicators. The way it works is you enter your task into your personal plan, into the tool. You then collect data that is automatically logged against the task, and it's collected in the tool. What you're usually working with is that skinny dashboard up at the top of your screen. To collect time data, you are just clicking on a dashboard control. Click to start or resume a task, and click to pause or complete a task. In each case, the tool's calculating the durations automatically and entering it into your time log. Now, like I said before, the most important attribute of any measure is that it drives action. Otherwise, it's of no value. Okay, so why do you care about tracking your time? Thank you, I thought you'd never ask. Look, time is your most valuable commodity. When you track your task time, you can learn from the data to improve your estimating and forecasting. Estimates become more accurate and more meaningful. When you make a commitment, you can feel confident that you will actually meet the commitment. Being trustworthy, being someone that meets their commitments, it's very important. It's the type of person that you want to work with, right? It's a valuable team member. Let's shift into a very simple example of how tracking time can drive action. Meet Joe, the software engineer. Joe has been coming in late with estimates on a regular basis, so he's going to see if tracking his time will help him. So he looks at what he needs to do and comes up with an estimate for how long he thinks it will take to code and test. He then starts the work, he completes the task, records the actual code size, and then examines his time log. Okay? Well, Joe is pretty surprised and not so happy with the results. He knows that he tends to just jump into coding because he feels that he can figure things out as the code emerges. But the next time, he is going to sit down with paper and pencil to map things out before he begins coding. He'll measure again to see if the change makes a difference. This is the result, okay? Compared to his previous performance, Joe learned that by incorporating some design at the beginning, before he started coding, things went much smoother. And there weren't so many difficult problems to fix during test. The one thing that occurred to Joe is that he would never have been able to compare his performance like this before because he had never tracked his time before. But with this type of data feedback, he is now feeling much more in control. And that's the thing about collecting personal data like this. It actually makes you feel empowered and it makes you feel in control. Joe took a further step. He started tracking his time doing a personal review of his code. Here's the data. He tracked his review rate against the % defects that he found. And what he found is there's this sweet spot. It looks like he should be reviewing at a rate at about 100 lines of code per hour. If he goes faster than that, then the review isn't as effective. But how would he have known this without measurement? He wouldn't have. So what about quality performance? We were talking about schedule. This slide is depicting a typical approach that we encounter all the time with software engineers. A software programmer being led around by the nose of their debugger rather than using data that is readily available from the work process to learn and to avoid making the same mistakes, rework over and over again. In this case, the debugger is in control of the work, not the developer. There is a better way. And that better way is to take an engineering approach and collect data that we can learn from so that we can become better at what we do. Using the same tracking tool that we talked about earlier, you can find a defect and start the timer, select the defect type, and record a brief description of the defect. The timer is stopped when the defect is fixed. It's all recorded in the tool's defect log. Now, you can view this type of data in various ways as generated by the tool. Here, the data is organized to show you which types of errors, which types of defects are causing you the most amount of time to find and fix. Again, it's a waste of time to collect measures if it doesn't drive action. The idea behind collecting the defect data is to help you find ways to improve your performance. A good way of using the data that we just talked about is to update your review checklist based on the defects that are typically being injected into your code and the ones that are causing you the most problems. That way, when you are in your reviews, you'll be sure to look for those types of defects in the future. And why do you want to catch them during your reviews? Why not just test them out? Well, our empirical data shows us that if you can find the defect and fix it in review, it's 20 times more efficient than finding and fixing it in unit test. And again, time is money. So that's the idea here. You use your personal data to learn and improve the quality of your work. You learn from your mistakes so that they don't keep happening. This is what performance improvement is all about. You use measurement to help you get better. So, in this section that I've talked about, we've emphasized that you, the software engineer, are a knowledge worker. As a knowledge worker, you need to take responsibility for managing your work, including how you make your commitments and how you control the quality of your work product. Measurement can most certainly help you. There are only 4 basic measures that you need to manage your work. So coming up, Bill is going to take the reins and describe how teams can benefit when they collectively agree to estimate and collect the 4 basic measures that we have just covered.
From Matt asking, how can you trust the data you measure when no 2 tasks are the same?
Well, I wish we had more time to go into the details of how this data is collected. But what we're doing is we're collecting time against tasks that are in our plan. And those tasks are typically organized into phases. We're grouping those into phases. And so what you're learning about is how much time do I spend on a task that's in, for example, the review phase, or how much time am I spending coding? How much time am I spending in test? More or less getting a handle over those types of things.
Stuff that's repeatable.
Stuff that's repeatable. Yeah. You're learning each time you're doing it. As you do this over time, you're actually collecting information, establishing a historical database that you can go back and take a look at, analyze, and make better decisions with.
Great.
So what I'm going to talk about is measurement at the team level. Mark talked a good bit about the measurement, the personal level, and we had a question about measuring tasks that are different all the time. Guess what? Variation happens. There's going to be a lot of variation from task to task, from instance to instance, from team to team. So part of what I'm going to show are some data that our partners have very graciously shared with us from their own personal data, so you can get a sense as to what are the real ranges of performance out there. Before we go any farther, let's talk about the differences of what we can measure now using this paradigm. If we look at the traditional project management, you could only measure what the boss could see. The boss had to be able to see it to measure it. By having the empowered team the people who define the process, who define the practices and measure themselves, measure the work, a whole new range of activities become able to be measured for the first time. Because the people doing the work can actually measure it themselves, and they can see things that the boss could never see. Now, it becomes more important. The more the work involves creativity, responding to change instead of following a specific fixed plan, but adapting your plan, intangible outcomes that can't really be seen, the greater the importance for the worker autonomy. That means the workers have to define the tasks. They have to define the work practices. They have to measure them. Management is still important. The manager has to provide the resources. The manager needs to have some idea of how many people we're going to need, how long this is going to take, what kind of facilities will they need. And management has to provide the direction. What are we trying to accomplish? What are the goals? But the teams now are responsible for defining the tasks to achieve those goals, for planning the tasks, for scheduling, for tracking the work. Now, we can see here that measurement now supports a feedback loop. You're going to define activities, you're going to measure the activities, and you're going to determine how do these measurements compare to what we actually expected. Now, meaningful feedback requires measurement. Measurement is precise and meaningful feedback against your expectations. That is, if you don't have some expectation going in, you can't be surprised. If you can't be surprised, you can't learn anything. Now, it also requires that you define your process and you have enough consistency in what you are doing that the measurements are at least comparable, that you're comparing likes to likes. The outcomes don't have to be the same, but they have to be similar enough that the comparisons are meaningful. Now, you can take these measurements at a number of different points in the process, and that's what we're talking about here. In a typical development process, you will have release cycles. You're going to have multiple releases of a product very commonly. Within the releases, however, you're often going to have development cycles, pre-release. You might have potentially shippable increments. Within the cycles, you're going to have individual components that you are building and maybe integrating into the system. Drive this all the way down and you have work that you're performing week to week, day to day. You can measure at each of these points and mark your progress. Now, as I said, it's essential to have estimates with which you can compare to actual measures. This provides you a closed feedback loop. Your estimate provides you a sort of set point. Your actual is what is actually happening. This is critical to the learning process. People learn by comparing what actually happened to what they expect, because when they get deviations from their expectation, they know that they can change their performance in certain ways by changing their behaviors. And this is what leads to performance improvement. This is how people achieve expertise and mastery of a subject. Now let's sum that up. We have an overall system, and we can measure it. We can estimate at the beginning, we can measure at different points, and we can do comparisons to see, are we on track? Have we achieved our objectives? Now, the good news is, as Mark told us, we only need a few simple measures to do all of this. If we measure the time on task, think of time on task as the stopwatch time when you actually have fingers to keyboard doing certain types of activities. The schedule is the big picture, milestones. When did something actually get done? Time on the calendar. The size, how big was it? Was this a little piece of work like a page, a sheet of paper? Was this a big piece of work like a book? defects. What did I have to go back and change after I thought it was done? What did I do incorrectly or wrong in a way that's going to affect my customer? From these measures, from these 4 simple measures, we can derive a number of other meaningful measures that can be applied in different points in the process. I'm not going to discuss all of these right now, but just 4 simple measures open up a world of other useful metrics. Now, what are you going to use them for? Ask questions. How are you going to do your work? What is a best practice? How do you know it's a best practice? Well, best practices should do what? They should get you good results. Compared to what? Compared to what other people are achieving. And that's what I want to share with you a little bit today. Some of the results that we have collected over the last several years. Our partners have been gracious enough to share with us the data that they have been collecting since about the year 2000. This particular data set includes data collected from roughly 2000 to 2012. We have in this set about 93 sets of projects or portions of projects from primarily the United States and Mexico. I'd be surprised if we don't have a few other projects in there as well, because we have some active teams in South Africa and Japan, Korea. But this particular set may be limited. We have tried to narrow the scope on these projects to projects that we know completed, for which we have post-mortem data, and we've put in a few tests to make sure that we didn't double count, that there are no duplicates. But this data was recorded by people, as Mark suggested, taking their own data for their own purposes, tracking their projects, and then sharing with us when they were done so that we can aggregate the results and give the community results back to them. So, let's talk a little bit about the demographics of these projects. How long were they? Well, how long should normal projects be? How long can your planning horizons be? We found that among our customers, the most common planning span was about 12 to 9 weeks. Now think about that. That's a little under 3 months. That's about how long they thought they could make a credible plan for. And most of these projects were a relatively short duration that would be completed in a single cycle. Now, that's not all of them. We found that about half the projects were shorter than 13 weeks. 13 weeks or less. What is 13 weeks? Turns out that is 3 months. It's about a quarter year. Half the projects were longer than that. In fact, a significant number of them were a half year or longer. Why do you need longer to build a project? Well, one of the answers might be the size. Now, we'll use lines of code to talk about project size. It's only one measure, and it's not a perfect measure, but lines of code, because people have to build them. These are only the lines of code that people actually make themselves. That tends to correlate with effort. You're limited by how fast you can create code. So it's a mix of different programming languages, different environments. We're seeing global industry benchmarks, not individual local numbers. This is a collection of all those local numbers. So take that with a little bit of caution. But what we have is a distribution of project sizes measured in lines of code. Now, what did we find? The median, that is, half of these projects were 6.6, and this is in thousands of lines of code. The median and the mode were both in this short bin here. 6.6 thousand lines of code. That's not all that big. It would be considered a fairly small project. To put that into scale, that's probably about what one individual could do somewhere in the year time span. On the upper end of a year, maybe, if you're writing new code, I've seen people do 10,000 or more. But that's about a man year of effort. The mean, the average, was twice that. So we're at about 12,000 lines of code. The average project was actually a couple of man years of effort. And we can see that there's a substantial number that come out much, much longer. Now, how much can one team actually write? So we have, these are the durations, this is the size of the projects. How are you going to staff it? How many people is this going to take? Well, let's take a look at team sizes. The most common team size that we observed was 6 people, a very small team. Many of you have probably heard some recommendations on 7 plus or minus 2 as the ideal team sizes. Do people really behave as though that's true? Well, most common team size is in that range 6. The mean size, the average, is on the upper end of that at 8. But about half the teams, a large number anyway, about a third of them, are much longer, are much larger, peaking at about 19. So we have a lot of fairly sizable teams out there that people have been trying to organize. So it's a fair question. Does the rule of 7 plus or minus 2 really make any sense here? Are these people hurting themselves by putting together bigger teams to try to get these projects done, bigger projects done in shorter amounts of time? How would you know? What kind of question could you ask? Well, we have some benchmark data that might help you think about that. What would you measure? Well, one measure would be a code production rate. How much code do people actually write? And this is the variance. We found a pretty substantial variation in how much code people are able to write in a given time. So we're going to measure this in lines of code per hour. So what is a reasonable number for lines of code per hour? Turns out the average is about 10. Just industry benchmark, 10 lines of code per hour. That's presumably from primarily in the development phases, but it could be from requirements through testing. The median was 7. So if you're organizing a team and you don't have any other information, this is a good place to start. If you have some idea of how big the project is, this is an average value, but here are the span of ranges. We see some that are much slower, much faster, and some that are much, much faster. What does your data look like in your environment? What kind of ranges can you expect? Here are some benchmark data. But let's get back to the question. Do large teams slow you down? If so, how much? We did a scatter plot of team size along the x-axis versus the code production rate along the y-axis. So each point represents one team and the rate at which that team was able to build code. We have the team size along this axis. Let's look at the data a little. We have a few very high productivity points. I kind of suspect some of that data might not be counted right. It's possible that some teams were counting automatically generated lines of code, or they had a very small project where they were able to build out something like HTML code very quickly. Those sorts of outliers don't happen with the larger teams. So I suspect these are smaller teams, certain classes of code, or some mistakes. But even with those accounted for, we did a regression fit. And we have a regression line, an average line, a best fit, that looks like it does slope downward a little bit. And we might have lower productivity. But what do these statistics say? The R-square, the correlation coefficient, is a measure of how predictable how much predictability this line gives us. R squared of 0.03 says 3% of the variation in production can be explained by the team size. So the answer is 3%, not very predictive. Whatever these teams are doing, the larger teams are more or less as productive as the smaller teams per person. So there you have it. That is the answer from what is actually happening in the field from this data. So what else? What else might matter?
What do you think is the average number of task hours that a team member spends during a week? Bill, any speculation what that answer will be?
Task hours is finger to keyboard. I don't want to bias the people in their guesses because I know the answer.
Okay.
But how much time? The question is, how much time, fingers to keyboard, shoulder to the wheel, nose to the grindstone, if you will, can you actually get on project work in a given week? Let's say a 40-hour week.
And we will share it now with our audience. Let me pull it back up to read them off. 30 to 40 hours we have at 5%. Okay. 30 to 35 hours we have at 16%. 25 to 30 hours we have at 27%. 20 to 25 hours we have at 26%. 15 to 20 hours we have at 12%. And less than 15 hours we have 13%. So quite a mix.
Okay. Well, some of you may not be surprised, but I think a lot of you will be shocked at what the real data is telling us. Where is the peak of this curve? This is my mean time, the average time per person per week. And this is my count. How many? So of these 111 data points, we took the projects, we took the hours, divided them by the number of people. How many hours per week did they really get? The most common was between 7 and 9 hours per week on task, on project. So less than 1/4 of the working week was actually on time, on task time. Now, the mean value, not much difference from the median. They really are both clustered at around 9 to 10 hours. We can see that there are a fair number in the 12 to 15 hour range. Not so many. We're actually running quite a bit out of this. Let me show you the lines. These two lines represent 50% of the data. Half the data is essentially between 7 to 14 hours. That means that about 1/4 of them are lower and another 1/4 higher. Now think about that for a minute. We can see that there are only a handful that are able to get 20 to 25 is the peak number here. Only a handful can achieve these sorts of on-task hour performances. Now, I've been there myself and taken my own data. In order to achieve these sorts of numbers, you have to lock yourself in a room with almost no interruptions and work with shoulder to the wheel all the time. You would be amazed, even in those conditions, how difficult it is to approach 30 hours per week on task time. Oh, what do you have to do? You have to do things like you have to spend a certain amount of time at the water cooler. You have to get up and stretch. You have to attend mandatory staff meetings. You might have to attend mandatory training. By the time all is said and done, there are a lot of demands on your time. And unless you understand those demands, you can't manage the task time. The problem is, the task time is the only time that really helps you directly advance your project. So what we find again and again repeatedly is when teams start falling behind, there's a desire sometimes to just move the goalpost. Well, this is as fast as we can work. But if you understand where the time is going with a little time management, you can actually get some help. And one of the things that's been very helpful is we've asked managers to do things like take the project team and put them in the back of the building away from everyone. Just isolate them for a while. What happens if you're working on 2 or more projects? That's a killer. What do you have to do to be on a project? To be on a project, you have to attend staff meetings. You have to communicate. What we're typically finding is that if you're on a couple of projects, that's how you get down here. By the time you're on 3 projects, you're lucky to get any time at all to work at all. That's what the data says, and it's really kind of surprising. Now, the good news, and there is some good news in all of this, is that if you've got a little historic data, if you have a little local historic data on what your environment is like, you can predict how many task hours you get. In fact, you can even work to improve it. And you got to be careful about that because task hours, task hours aren't your objective, but they give you a lot of insight into where the work is going, where the time is going. This R squared is the correlation coefficient for this regression line. R squared, 95%. For teams that have measured their time, have some historic data, and have made some projections and managed their time, their actual effort has a 95% correspondence to their planned effort. So they bring this under control. So that gives you a whole new dimension with personal measurement of how you can take control of your schedule and stop being tossed about by the winds. So the sum of that is the actual hours are what really go into your project, and you do have some ways of measuring and controlling them. Now, that takes us to the issue of quality. And it looks like I do have enough time to go through some quality slides. So I'm going to talk a little bit about quality. One should never talk about schedule or production without speaking to quality when you're talking about knowledge work. Knowledge work is not a commodity. We are not talking about widgets coming off an assembly line. Every widget is different. That means you have to evaluate the quality of every widget. Was it correct? And if it wasn't correct, you have to go back and rework it. Now, what we find in the software world is you measure that primarily through defects. Guess what the most consistent process in software engineering is? Injecting defects. Humans make mistakes. We make mistakes remarkably consistently. We do the same things over and over. If you're building a project, you are going to have defects. Removing them, that's another matter. Removing defects is optional. You don't have to take them out until someone complains. But if you're building it, you have to inject them. In fact, we have the data here at how fast the different teams have injected defects. And we can see this range with a peak of about 55 defects per 1,000 lines of code. We can do that also in defects per hour. So, the error is human. You will make defects. Live with it. But defects are predictable. Now you must make a plan. The reason you need to have personal plans, when you know what your defect injection rates are, you have to make a plan to get them out. If you don't plan to get them out, they aren't going to get themselves out. So that's why we have creation phases. We're creating product. Separately, we're going to have phases to remove. We can remove defects by doing personal inspections or personal reviews. We can have peer reviews or inspections. We can run tests. You have to plan for the removal phases. And you will have more than one. You'll inject defects when you do requirements gathering, when you do designing, when you do coding. So they have to be followed by various types of removal phases. And that's what I'm going to show here. There are many other ways that we can examine the defects, but I'm going to look only at the defect densities. What are your expectations going in? What are the expectations about how many defects are going to be in your product at different times. So what I have here, defects that were removed during design reviews. Here we have defects removed during personal code review, during peer review. And we can see the defect profile. The scales, I'd prefer if they were all at the same, but we can see the profiles narrowing as we get deeper into the process. Then we have various types of testing phases. And you can't quite see the scale here clearly, but here we have a peak of about 8. As we get into later test build and integration, the peak is getting closer to 1 or 2 defects per 1,000 lines of code. And in system test, this peak here is actually less than 1 for these particular teams. Here are some of the numbers that we have measured as average benchmarks. So in unit test, we suggest that they try to get under 5 defects per 1,000 lines of code. In fact, these teams were measuring as a group, averaging 3.8. We recommend less than half a defect per KLOC in build and integration. These teams on average were around 0.7. We recommend that would be 200 defects per million lines of code, to put this in perspective. Industry standards right now, you typically see 1 to 5 per 1,000. That would be 1,000 to 5,000 defects. We're recommending 200. And what are the teams achieving? On average, 150 defects per 1,000 lines of code in system test. Now again, some perspective. What we find is in the field, in industry, shipped, delivered products are typically in the 1 to 5 defects per 1,000 lines of code. If you have applications more like, say, your phone app, probably closer to 10. But that takes us to the download side. We have this benchmark data and much, much more. We can only scratch the surface in this time. And I'll leave you with this message from Edwards Deming. In God we trust, all others bring data.
Question for Bill from Michael asking, does a process methodology, for example, Agile or Waterfall, affect time on task?
I don't think we've seen any distinct measures on Agile versus Waterfall per se. It would be kind of hard because we haven't seen the many of them instrumented. We have had some Agile projects instrumented though. Frank, let's see. I guess we could compare. I can't go into the company names, but I do know some specific ones. I haven't seen anything that jumps out at me, but it's a good question. I'd have to look at that.
Okay. One from Mark, I believe this was from earlier, from Hilla asking, for the projects in the sample, were they purely software? In other words, is firmware included? What is the end product? Is it purely software?
Purely software from those projects, yeah.
Okay, question from Bradley asking, are the team counts for just for developers, or do they include others, such as BAs and testers? I believe this was from earlier. Are the team counts for just developers, or do they include others, such as BAs and testers?
In this particular set, it's including all team measures, all team members, depending upon the nature of the project. If it was only the development phase, typically it was developers, but several of the projects do have testing specialists and requirements specialists. So it's a mix right now. We haven't segmented the data down to that level.
Okay, great. Darren asks, with the higher lines of code with smaller teams, was there a correlation with defects?
We have some data on that. We haven't looked at the production rates versus defects, but we did not find any correlation with defects and size of team.
Mm-hmm.
Okay, Matt asks, this was from a section with Bill, if the time spent on task is so low, what else is taking up the time? He mentions, is it YouTube?
Mm-hmm. No, actually, I personally taken my own data, and literally I used to work in a vault. It was literally an old vault in the back of it. So people weren't coming by and interrupting me. And the peak times I was able to hit with absolutely no interruptions, just coming in the morning, sitting down at my computer, turning it on and starting to work, were 28, 29 hours. I might have cracked 30 once. So with absolutely no interruptions, that is like an absolute upper limit.
Yeah, I really encourage people, just as an experiment, try tracking your time for 1 week. It's really going to blow your mind. You're going to actually see, firsthand that where did that time go? It's a real eye opener. It was for me. I still track my time, and I'm always kind of surprised. It makes you much more aware of how you're using your time. Yeah.
Well, and it's more practical. If you have like a staff meeting, it's not just that hour. You have to get ready for the meeting. You have to walk back to your desk and start. By the time I've started my clock in, it might be a half hour past the meeting time.
Yep.
Okay.
Amazing. Yeah.
Next one from Mike asking, at the team level or at the division level, what are some best practices in terms of software metrics collected and reported that answers the question, how do you know as a software organization we are getting more efficient?
Well, that's a tough question, because if you're talking about efficiency, but the single best efficiency measure that I would use would probably be cost of quality. How much rework are we putting into the product?
Mm-hmm. We got about 30 seconds left. Let's fire off one more question here. And this is from Hila asking, what is the difference between code review and code inspection? We'll wrap up with that.
You want to take that?
Oh, sure. Well, code reviews are considered personal reviews. That is, before I perform unit tests, I'm going to sit down, look at my code, and go through it, do a personal review of the logic, of whatever defects might be in there. A peer review or inspection is when you have multiple colleagues that's looking at and inspecting your code, looking for defects from their various perspectives. So that's really the difference.
Excellent.
there.
Mark, Bill, thank you very much. Great
yeah,
presentation. Everyone, that's our time for today. Again, I know we had lots of questions we weren't able to get. Please go to LinkedIn, search under groups for measurement and analysis, post your questions there. We'll get to as many as we can. And lastly, I just wanted to invite you all to submit a proposal to the Team Software Process Symposium, which is set to take place in November in Pittsburgh, Pennsylvania. The technical program this year will go beyond the core methodology of TSP to encompass a broader range of complementary practices that contribute to peak performance in software and systems projects. And the unifying theme this year is software quality.